Good evening and welcome to the live sessions for the course on Fundamentals of Additive Manufacturing Technologies. It is 6 p.m., but participants are yet to join. So we will wait for a few more minutes before we get started. Thank you.
So the college was closed. Yesterday you could travel?
Yeah, I went.
Okay.
The city gate.
From local. That's it.
Actually, they declared holiday
After you.
2 p.m.
So Saturday will be.
Yes, sir.
Okay.
Yes, sir. Writing.
Sorry?
Writing.
Yeah, sure.
Writing.
So, sir, I am ready for evaluation in the research results. Even after seeing time steps, I was having that acknowledge issues.
What's central difference? Video
Yes.
central. Okay.
So, I think it is mainly because the pressure and velocity are not coupled properly over the phase change. So, there I am changing the tolerance values and I will show it in the
Okay.
finally, by using smooth feedback, we started learning some material.
I got this. So I am in different K1.
Okay.
So
Okay. Better.
the different K1. Same the new that
Right.
now and overall yeah. So I will also I'm running multiple
Yeah,
others.
see the other thing is your CA simulations are in a small domain.
Yes.
Right? So the fluctuations are likely to occur in the stress strain curve. Whereas the actual bulk sample in data will always be averaged out.
Yes.
So what you should do is if you get fluctuation, do moving average and then report. And then you also state that you have done a moving average because this is now a right?
Okay. So this is the written method.
So that is okay. I mean, I am pretty sure others would have done it because any micro model would involve the fluctuating because you're looking only at tens or hundreds of grains as opposed to a bulk behavior which has millions of grains.
Okay. I'll increase the domain size again.
If you can at some point, but I think even while reporting you can report moving average.
Okay.
Yes. Otherwise it will not get you a micro domain.
Okay.
Properties.
Okay. You can project on so that he is not ready.
Oh yeah. So
Yeah, I called him actually.
okay. Grains. Yes. Fine. After discussion. So you know his setup? So that it was okay. Just be ignored with the experiment. But at some point you might get some data to validate all that. So is elimination that's
I called him.
okay.
I also called him.
So no, we have to streamline because he has to generally give some what I'm proposing is maybe one weekend or something we have a common meeting.
Yeah, that is good.
So then we discuss and whatever he has to hand over and review to the
I called him, but I don't know if you already called back.
I messaged him like which he told me like it's there is something what is your problem.
so let's avoid intermittent this thing. One fixed time in a week.
Yes.
Let's set up a meeting. Sure. The CS will not have a rough idea. Then you know in coherency if they are interlocking, whether the rates will sustain or not.
Please sustain. That will be the numbers. The numbers will come.
Yes. They might not even have that process for now. Even if you ask, why is the complicated explanation? Sir, see, this is the equation. All you have to do is, this is the first. So this is either coming from some physics of motion of solid, or it is coming from any assumption. What would be the assumption? Assumption can be stationary. So if for it's a stationary porous medium, Vp is zero. Now, if porous medium is moving with flow, Vp is u. Okay, so then it is zero. In third case, if Vp is coming from some physics, let's say we so we have three case conditions, and one of them will apply to this, and therefore accordingly this stuff that would be very
Good evening and welcome to week 4 of the live sessions for the course on Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajan Kapil, who is a member of the faculty in the Department of Mechanical Engineering at IIT Guwahati. And I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. The course contents for this week dealt mostly with stereolithography and in particular with the subsystems of stereolithography apparatus on laser beams, uh, lasing mechanisms, and on the mechanism by which such a laser beam cures the resin, which is the liquid feedstock used in stereolithography of SLA systems. And we looked at uh, the working principles of single bead curing, multi bead curing, and were very briefly introduced to multi layer curing. Over the past few weeks, we have been discussing the fundamentals of additive manufacturing. We looked at the definition of the process, what are some of the typical processes, what are the categories into which all such additive processes have been classified. We looked at some basic computer-aided process planning steps, which concerns the pre-processing part, while we are still sitting at our computer working on our design. Or if we have a design, we make it say suitable for printing by tessellating it. We find and check for any necessary support structures which may have to be generated along with the build material. We saw how by the how 3D model is divided into various slices, and how by the intersection of these the tessellated object with these slicing layers, the contours are generated, and how these contours are filled. What are some of the considerations and some of the strategies to fill these contours? Now and for I think the remainder of the course will actually be dealing with actual 3D printing processes which are already commercialized and put to use uh, for say commercial manufacturing as well as R&D purposes. Uh, as some of us might be aware, the very first 3D printing system to be invented and commercialized was the stereolithography system. And in terms of its subsystems, it uses galvanometer, as we already discussed towards the end of last session. The shape of the UV light is in the form of a laser beam, as opposed to say a floodlight. The shape of the liquid is in the form of a liquid vat. The build direction is along the plus Z direction, and the recoating system was originally deep dipping, but as we saw, because of the requirement of a large amount of resin at all times in the vat, which is inherent to deep dipping, later the technologies of top feeding and bottom feeding came into the picture. So the original SLA system developed by 3D Systems used a galvanometer as a scanning system, laser beam as the UV light, had the liquid resin in a vat, built along the plus Z direction, and used deep dipping The improved and comparatively modern Zephyr system again used galvanometer, laser beam, had the liquid in a vat built along the pressure direction, except it uses the top feeding mechanism. Professor Kapil already described this video describing the working of a 3D systems SLA machine. Just like any other AM process, also with SLA, the three major blocks of steps are pre-processing, the actual building process, and okay, post-processing. As I was describing in the pre-processing step, we make our 3D CAD model ingestible by the 3D printing machine. We can slice it directly or indirectly. We tessellate it with some chosen shape. We check whether support structures are needed, and if they are needed, where. We choose the material for the support structure in case there is an option to have multiple materials being printed in the same print. If not, we specify the density or the infill structure or any other such distinguishing mechanism, even the color for the support structure. And then typically in commercial systems and in SLA, we perform planar slicing. During our discussions, we also looked at some of the more exotic varieties of slicing, mostly conformal or non-planar slicing, but it's not commonly encountered in SLA systems or DED, in which I work. Now, during the build process itself, the table or the build table goes down by the required layer thickness, and since the table and any pre-built material is already inside the liquid vat, the new layers of liquid are recoated, and in SLA it is done by deep dipping. Once this is done, the stage will again come towards the top and will retain just a very small amount of resin which is required for the building of the immediate next layer, and that amount or that layer of resin is then scanned by the laser beam. Now for each contour, first the perimeters are scanned or the border is made, and then the area filling is done. As we had discussed, the printing of the perimeter of the contour is a precise operation, and so it may use a smaller diameter laser beam or in some cases a smaller speed. Say typically in metal wire DED, the printing speed for the perimeters is only 90% of the actual programmed value, whereas compared to the infill. Now, once we are doing the area filling, well, this also has to be precise, but then the requirement for precision is less than when we are printing the outer contour. That is because now your outer perimeters are already established. So, just for an example, we first print the perimeter in a contour. Typically, you can have say two perimeter layers. And once they are printed very precisely with say a small a spot size, we can then do the infill by any of the processes such as by the zigzag process, which we discussed in one of the earlier sessions. Of course, I'm showing these single lines, but we know that excuse me, yeah, I'm showing the single lines, but we know that when we're actually printing the material, it will not be just a line. It will in fact be a bead of some finite width. What this single line path indicates is actually the position of center of the laser beam, and this infill operation would be done typically say in the case of SLA with a larger or coarser beam size, or in some cases at higher speeds. After all the layers are made, the table will rise completely revealing the part. So this layer by layer printing process occurs iteratively. The contours in each layer may be different. In the case of complex geometries or for very simple prismatic geometries, they may be the same. However, once all such layers are printed, the table will then rise to reveal the part and allow the liquid to be drained. Once all the liquid has been drained, the built part will be removed from the table, and then this removal process, uh, say depending on the type of process you're working with, if it is FDM, it can just be removed by hand or by some knife, which is used to separate the printed part from the build plate. Or say if it's a metal part which has been printed using powder bed fusion, then it will need to be separated, say by a wire EDM process, or by some kind of abrasive grinding process. And further, the support structures have to be carefully removed. Why do we have to take care for removing the support structure when we know that the support is a sacrificial material? That is because while the support is indeed sacrificial, our built part is not. And since the support structure is connected to the build part, as we discussed, there may be cases when the support does not really project onto the build plate itself, but from one surface of the build to the other surface of the build. Thus, the support can be connected to the build material at multiple places, and if we are not careful in removing it, it can leave remnants and damage the surface finish. Secondly, as we had discussed last week, at this stage, the printed part is not at 100% strength, as in it is still green to a certain extent, and thus it is still weak. It will be cured only during the post processing step. So, at this stage, if we are not careful and we apply too much force, we can even end up damaging or breaking the build part. Now, in the post processing step, the part is kept in a post cure apparatus, typically something like UV chamber, where it is kept under UV radiation for complete polymerization. This can take anywhere from say 30 minutes to a couple of hours, depending on the build size, the intensity of the laser, and other factors. And finally, once the part finishes curing, it is finished, taken out, and may even be further painted if required. Here we have a brief summary of some of the advantages and limitations of the steel lithography process. It is among the fastest and most accurate of all processes. The reason for the great speeds are because of the tiny moving parts, including the scanning system, which is made up of galvanometers. Galvanometers, as we are aware, consist of a pair of light mirrors which are mounted onto motors. And because of the very low inertia of these mirrors, the motors are able to rotate very quickly and uh, uh, say scan the print area with the laser beam at great speeds, say typically at the speed of the order of 10 meter per second or even more. And it is accurate for a couple of reasons. One is because of the fine size of the laser spot which is used in this process. Second, because since it was the first 3D printing system to be commercialized and developed, a lot of research and a lot of efforts have gone into perfecting this process. And thus, for most available resins, we already have a set of well researched and well tested uh, optimum operating parameters and strategies, the combination of which leads to very good parts with great accuracy and tolerances. Second, it has the capability to print transparent parts and with very fine surface finishes, which are ideal for applications such as photoelasticity. And there's this special subsystem of an SLA type process called quick cast, which can also be further used for producing castings for any metal. However, all is not rosy, and there are certain limitations to this process. Uh, it is comparatively expensive, uh, say compared to other processes such as maybe metal extrusion, 3D printing, or FDM type processes. The parts which are built by SLA are, as you remember, starting from a liquid feedstock, are made out of resin and then built by polymerization using a ultraviolet laser. Now, even visible light has some component of UV radiation in it, and so when a part built by SLA is exposed to just ambient atmosphere and ambient lighting, it continues to polymerize, and thus over a period of time, it will turn brittle. Only photopolymers can be processed by this route. It can be used for the processing of, say, metals or ceramics. And the machine is not really suitable for keeping in an office-like environment because it emits a lot of fumes, which are hazardous to health. Here again, we have a pictorial representation of the build process for a stereolithography apparatus. The laser beam is used as energy source and it scans the selected region over a layer of liquid photopolymer to cure it. The power density of the laser spotting material properties govern the curing process, as we'll also see in the upcoming slides, where we actually work out the actual mathematical relationships between, say, power density, material property, the depth which is cured, and so on. The laser beam is scanned using galvanometers, which are shown here. So this is just one galvanometer, but as we'll see maybe in the next session, there's actually a pair of them. And galvanometers are having a very low inertia, which accounts for the very high speeds. And then the recording system is used here and is also shown. So the existing layer of resin, say a very fine layer, is scanned by this laser, and then the stage goes down, allowing for all of this resin on the sides to come up and flow over the part which is already partially deposited. Now resins are typically very viscous and this flow will also be turbulent, and so it might take some time before the top of the build part is amply covered by the existing resin. Uh, it may also be seen to bulge on top of the part, and to ensure that there is only a uniform layer of required thickness on top, we use something called a doctor's blade to scrape off the excess material, leaving only the required height or the required layer of resin on top. And then this process continues. The next layer is scanned and so on. Professor Kapil also discussed some basics of the lasing process. Laser, as we are aware, stands for light amplification by stimulated emission of radiation. Light is any electromagnetic radiation which has the dual nature of waves and particles. And if you're talking about the particle nature of light, then the quantized light particle is called a photon. All types of electromagnetic radiation travel at the same speed in vacuum, but where they differ in is in the frequency and wavelength of radiation. And because of this difference in wavelength, all different types of electromagnetic radiations interact with materials differently. If I have to give example from additive manufacturing, we know that for ceramics, the suitable wavelength is often say of the order of 10 micrometers or so for laser. Typically this will be of the CO2 laser type. For say regular Fe, Ni or Ti based alloys, uh, lasers with wavelength of the order of 1 micrometer, some 976 nanometer or so are suitable. However, these will not work for other metals such as aluminum or copper, and that is because of their very high thermal conductivity and very high reflectivity. So, for materials like aluminum and copper, these days you have say blue and green lasers, so their wavelength will be typically of say 400 to 500 micrometer. Blue laser is already well established, and green laser also up and coming. So, because of the change in wavelength, the interaction of the same electromagnetic radiation can be different with the different materials. Lasers have the property of being monochromatic and coherent. When we say monochromatic, what we are saying is that all Uh, for a laser beam, all the light waves will have the same wavelength, thus the same color. For the case of stereolithography, this wavelength falls in the ultraviolet range, and the laser beam will be coherent. That is, all of the individual light rays inside the beam will be in phase. What that means is, say, you have two laser beams, but it's not necessary that they will be in phase with each other. One can lag or lead the other one. And if the light rays are like this, then their interaction may lead to constructive or destructive interference. However, in the case of a laser beam, all the light rays are always in phase. Further, they are traveling in the same direction. So here we have the example of say, light emitting diode. So a red LED, where even though all the rays which are getting generated are in phase, but they may not be traveling in the same direction. So to summarize again, laser has a property of being coherent and being monochromatic. We'll not talk about the mechanism of laser generation. Professor Kapil has already discussed it. Sorry about that. Yeah. But we'll take a minute to discuss these transverse electromagnetic modes. Uh, there are two modes of the laser beam, one being the longitudinal, which we are well familiar with from the analysis of vibration, where we describe the modes of vibration of any, say, string or rod or any other such example. And second, we have the transverse mode. The longitudinal and transverse modes are independent of each other, and the reason for that is because this longitudinal length L of a resonator will typically be much larger than the transverse dimension, and we can have various transverse electromagnetic modes, which essentially describe the shape of energy distribution in the beam cross section. This is denoted by the subscripts x5 and x denotes the, say, the number of non-illuminated regions along the x-axis. Y does the same for y-axis. And so when you are given a number TEM x5, what it is trying to tell you is that there are certain regions along the cross section which are not illuminated, and this x is the number of such sections along the x direction, y is the number of such sections along the y direction. So if you have a TEM00 beam and the original beam shape was circular, then you end up with this first profile where all the regions are well illuminated. If we have a TEM10 type of mode, then what we can see is that along the x direction there is this one region of non-illumination. Similarly, for the case of TEM31, again, what we can observe is that along the x axis there are these three regions which are in fact non-illuminated, and along the y direction there is this one region which is not illuminated, leading to this beam shape. And of course we can combine any number of them to come up with new beam shape depending on the say end application, such as we have a ring or donut shaped laser beam here, which is made from a combination of TEM10 and TEM01. Similarly, we can combine different modes to come up with, say, top hat ring as we have here and other shapes. And the parts printed by these different laser profiles can have very different properties. However, what we're interested in is how this laser energy is distributed and how when this laser will shine over a layer of liquid resin, how will it interact with the resin and how will it lead to curing of the part. Uh, One of the uh, say most commonly encountered representations of laser power intensity is the Gaussian intensity distribution, which is described here. At any radial distance r, the intensity IR is equal to I naught into e power minus 2r square by w square. Here IR, as I said, is the power intensity at a radial distance r. Its units are watt per meter square. I naught is the power intensity at the very center. So this is at r equal to 0. And W is that particular value of r or the magnitude of r at which the power intensity drops to 1 by e square of I naught. Another name for this Gaussian distribution is also the bell curve distribution. So some of you might be more familiar with that, or the normal distribution. To calculate the total power contained within Gaussian beam, we can do a simple integration step. Starting with a ring of a laser at a particular radial distance r, the thickness of that ring being dr, we can find the power in the strip to be IR times 2 pi r dr, where 2 pi r dr is the area of this ring. So if we just say cut this at some region and spread it out, it will become a rectangle whose length will be 2 pi r and whose thickness will be dr. So this is just the area of this ring. And to find the total power, what we can do is we can integrate this elemental power uh, starting from r equal to 0 going till the end of this radial distance. But what is that limit? As we know, for a bell curve distribution, while visually it might appear that the distribution is say ending at some finite distance, what we know is that essentially this distribution extends till infinity in both directions. And so the limit of this integral also goes from 0 to infinity because the laser ray is actually spreading out till infinity. And thus we can come up with an expression for the intensity at a radial distance of r given by IR equals 2PL by pi w square uh, e power minus 2r square by w square. The laser beam after coming out of the lasing cavity is highly collimated. Collimated as in it is parallel, it is neither converging nor diverging, and its diameter does not really change much. However, that is for the very ideal case. In the more practical setting, the laser beam will diverge to a very small extent, and this is a slight divergence in the laser beam, and this is captured by the beam quality parameter BPP. It is quantified in the units of mrad, and there's a unit definition. So a 1 millimeter diameter beam will have a diameter of 1 meter after traveling a distance of 1 kilometer. Then its divergence is quantified as 1 mrad. However, there might be systems where the beam is again further focused using other focusing lenses such as f theta lenses, as we'll also encounter in our discussions, and then the scenario will of course be different. There's the concept of waste radius. So during 3D printing, when we say that we are focusing our laser say at a particular height, whether that is on the substrate or some pre-deposited layer or at some specified distance, it's never really this set of rays coming and closing in on a point, say when joining at some point. What actually happens is the laser beams will converge and diverge, and this uh, minimum thickness of the laser beam is referred to as the waist. It is quantified in terms of the waist radius. For an ideally Gaussian beam, the waist radius is equal to 2 lambda by pi theta, where theta is the divergence angle as shown in the figure here. For a real beam, however, it will further be multiplied by a factor of m square to account for the beam quality. So, some numerical examples were already discussed by Professor Kapil in class. We'll also discuss a few numerical examples of our own, which will be useful for solving the assignment problems. Next, we talk about the mathematics of the stereolithographic process, and we'll be dealing with a lot of equations here. However, they are well derived and well described by Professor Kapil, so we should not run into any issues. We'll just briefly recall some of the few important ones, which will be useful for our problem solving exercise later on today. So, say we are scanning a region, and for one particular bead, this bell curve shows the intensity of the laser profile. The directions of the x and y axis are shown. A scanning is happening along the x direction, y is the literal direction, and the z direction is pointing inwards. So this is a left-handed coordinate system, and we are scanning along a length of 2L from a time t1 to t2. So the intensity of the laser beam spot in units of watt per meter square on the top surface of the resin. So we have set z equal to 0, can be defined as I equals 2p naught by pi omega naught square e power minus 2r square by omega naught square. Here omega naught is actually the beam radius. The total exposed energy per unit area of the surface of the resin, again on the surface only with z equal to 0, can be defined as integral of this elemental energy for the time for which the laser is shown. And if this energy is falling from time t1 to t2, we can plug in these limits to find the total exposed energy per unit area. Now, during this exposure time, we assume that from time t1 to t2, the laser has scanned a single bead along the x direction as already shown in the figure, and it has let it scan from a distance of minus L to plus L, thereby making the total length of the wet to be 2L on the surface of the resin at some fixed velocity Vx. Then we can substitute the variable dt with dx by vx, and instead of time limits, now we plug in length limits and end up with this new expression for energy distribution along the y direction at a fixed x on the surface, so z equal to 0, as E at y comma 0 is 2p naught by vx by omega naught square e power minus 2y square by omega naught square integral from minus L to L e power minus 2x square by omega naught square dx. However, this might not really be so trivial to solve for the limits of minus L to L. And here we can do something really clever and actually substitute these limits for something which is more conducive to integration, and we'll see how we do it. So it has been observed that the laser exposure is proportional to e power minus 2x square by omega naught square, as we just saw. However, being an exponential function, that too of x square, this function will fall off very rapidly with increasing x, And because of this rapid fall, a term called the zone of influence is defined. And this zone of influence is the zone where 99.9% of the energy exposure will be received. So essentially, almost all the energy of the laser beam is contained within this small zone of influence. For strictly theoretical purposes, it is 99.9%, whereas the remaining 0.1% will be outside the zone of influence. And thus, we can calculate what will be the extent of this zone, and it comes out to be uh, 2.146 omega naught, or 99.9% of all the laser energy will fall within just 2.146 times the beam radius. For SLA system, a typical beam spot radius length scale can be taken to be 100 micrometers, and thus the limit of the influencing zone can be seen to be from minus 214.6 micrometers to 214.6 micrometers, or approximately just 500 micrometers. So 99.9% of the energy is contained within this zone only. And essentially, the reason for doing this exercise is, now that we see that all of the energy is only contained within some 500 microns of a low Hall region, it does not really matter whether we are integrating from minus L to L, or minus 2L to 2L, or minus say 100L to 100L, or minus infinity to infinity, because the amount of error will be very small. And out of this convenience, we simply take the limit of integration from minus infinity to plus infinity, which allows us to come up with a closed form solution for this integration. And so our equation is suitably modified. Now the energy distribution in the y direction for a given x value and on the surface with z equal to 0 now becomes equal to 2p naught by vx by omega naught square e power minus 2y square by omega naught square integral now from minus infinity to plus infinity e power minus 2x square by omega naught square dx. Recollect that the limit of this integral was earlier from minus L to plus L, because we have defined that the laser is only scanning along this distance. Now with some further suitable substitutions, this can be simplified to give us the final relationship. The energy distribution in the y direction for a given x and on the surface is equal to under root 2 by pi p naught by vx omega naught e power minus 2y square by omega naught square. But this was just at the surface. What happens inside? Because as we know that for the material to be cured, the laser has to penetrate into the bulk of the material. So when the laser beam strikes the resin surface, some of its energy will get absorbed, some of it will get transmitted, and some of it will get reflected. Because of the absorption, the exposed energy will decline along the depth z, which in this case is into the layer of resin. And thus, according to the Beer-Lambert law, the available energy at any depth z can be given as an exponential function E at y comma z is equal to the maximum intensity at y comma 0 into e power minus z by dp, where dp is defined as the penetration depth. How is dp defined? Again, mathematically it is defined at the limit for which the energy intensity decreases to about 1 by E, or 37% of the incident radiation. And we also have some numbers here. So typically this penetration depth value will lie between 0.14 to 0.18 mm, or typically of the order of 0.2 mm. Thus our final equation, now for the energy distribution at uh, any y and z at a given x, is now under root 2 y pi p naught by vx into omega naught e power minus 2y square by omega naught square e power minus z by dp. Now some comparison of scales here. Let us say that we are working with an SLM process, and we have some optimized parameters which we use to build parts. But say one day the idea strikes us that I want to save on build time. I want to build really fast, and my machine has the hardware capable of very high scanning speeds. So say you want to increase the scanning speed to some 2x or 3x or even 10x. And the rationale being that now if we scan faster, we'll be able to save print time and build faster. But what is the physical consideration that actually dictates the maximum speed that you can take? Or can you just go on increasing the speed monotonically and have any arbitrarily high speed of scanning? Is it only limited by the hardware? For that, here we have some time scales. The first time scale, TL, is the time taken for a single photon to pass through a single resin layer of given thickness LP, and this time will be equal to the layer thickness of resin LP by CR, where CR is the velocity of light in this given resin, and its typical order will be of picosecond, which is 10 to the power minus 12 seconds. This is the amount of time taken by a single photon to travel through or pass through a single resin layer of some given thickness. Uh, as we discussed in the last week, the process of polymerization actually involves cross-linking uh, that follows free radical generation. And the time for this cross-linking process uh, in the conditions typical of stereolithography and for the typical resins used is typically of the order of microseconds. This is given by Tk. So Tk is of the order of microseconds or 10 power minus 6 seconds. Now, the time needed for the laser exposure to reach 99.99% of its value when a Gaussian beam is scanned at a constant velocity past a given point is called the characteristics exposure time, TE. And the typical range in SLM of this time, uh, in SLA, stereolithography, for this time ranges anywhere from 50 to 2000 microseconds. That is zero point 0.2 seconds to 0.05 seconds. Microseconds. So this is some 50 to 2000 microseconds. So this is at least 50 to 2000 times more than the time scale for cross-linking, which itself is some 10 to the power 6 times more than the time taken for a single photon to travel through a single layer of resin. Thus we see that we cannot simply keep on increasing the speed of the process arbitrarily. Uh, what will happen then is that while we are scanning at very high speeds, the resin will not really get cured and we'll end up with a very weak part or one which is simply uncured, and the liquid resin remains as is. Now that we have a distribution of the energy inside the surface, below the surface of the resin in the bulk, we are interested in knowing the distribution or the shape of the cured part. So what we can guess is that there will be some critical threshold of energy intensity, E critical, which must be exceeded for the part to get cured. If the laser exposure is below this critical value, the part will only be partially cured or may remain fully uncured and in a liquid state. Only when this critical value of the energy intensity is exceeded, and only in those regions where it is exceeded, will the resin actually get cured. How do we get all those locations? Because the location of where the energy intensity is just equal to this critical intensity will give me the perimeter or the shape of this cured region. As I know, everywhere inside it, the energy intensity will be equal to or more than this critical energy. To do this, we simply equate the energy expression of the energy uh, with the critical value, and this will give us the expression for z at a given x in terms of y. Z will equal minus 2 dpy square by omega naught square plus dp ln under root 2 by pi p naught by bx omega naught ec. This is of the form z is equal to minus ay square plus b. So as we are aware, this is the equation of a parabola. If our leading coefficient were positive, this parabola would have been convex upwards. Because it is negative, oh sorry, it would be convex up. For a negative leading coefficient, it will be convex upwards. For a z direction which is pointing upwards, in our case the z direction itself is pointing downwards, and so our parabola looks like this, which is the expected shape of a cured bead. Further, the maximum exposure, which happens right below the center point, corresponding to the deepest location of the cured bead, or in some other processes, corresponding to the deepest location of the melt pool, can be given by Emax equals under root 2 by pi p naught into Vx omega naught. And the maximum curing depth at this maximum exposure can be obtained at y equal to 0, as we just saw. At this point, we have both x and y equal to 0. Sorry, at some particular x, we have y equal to 0. And if we just substitute that in our equation for the depth, this maximum depth can be obtained as CD, maximum curing depth, equals penetration depth into ln Emax by EC. And here are a few important observations summarized about these things. So the resulting curing depth values are plotted against the maximum exposure Emax values on a logarithmic scale, typically log 10 Emax. Since the magnitudes of dp and ec are constant for a given resin and for given wavelength of laser, this semi-logarithmic plot should yield a straight line. And these straight line curves for various parameter combinations are called working curves and are typically used or referred to directly when working with an SLA system instead of calculating them always by ourselves. So for the given standard resins that you use and for the wavelength of your system, you will be provided with a booklet containing these working curves, which you can refer to when trying to print a part. And this curve is usually experimentally determined through single bead laser curing experiments conducted in the range dp less than CD less than equal to 4 dp. And the reason for this is because in this region, the CD versus or Emax versus CD curve is straight line and shows linear behavior. Beyond this region, it can have a super logarithmic or sub logarithmic behavior, as we'll just see now. Trying to obtain a cure depth smaller than the penetration depth itself is usually undesirable owing to weakly developed properties of the cured layer. On the other hand, The working curve usually becomes non-linear when a cure depth much larger than 4 dp is attempted. An example curve is shown on the right here, which shows super logarithmic behavior. Uh, if we were to just extrapolate this curve, we would have expected this uh, straight line nature to continue, but instead we see that the slope has become much steeper. Uh, since the plot is already say semi-logarithmic, and this the given curve is now even steeper than a logarithmic curve, thus its behavior is called super logarithmic. And there are two possible mechanisms which have been proposed in the literature to explain such a behavior. One is optical bleaching, and the second is optical self-focusing. What happens in optical bleaching? The partially solidified part may become transparent for the laser, and hence, because of this transparency, it is now allowing a greater penetration of the laser into the system. As we know, typically it would have been controlled by Beer-Lambert's law, but now that it has become transparent to the incident laser radiation, the laser can now penetrate to a far greater depth. But what is this depth? It is just the slope of this working curve, and if this depth increases, there will be increase in positive curvature of the working curve, and we'll observe this super logarithmic behavior. A second mechanism is that of optical self-focusing, where polymerization results in the shrinkage of the cured part, and hence density will increase, which increases the refraction index. So, as we are aware, when light is traveling from one medium to another, if it is traveling from a rarer medium to a denser medium, it will bend towards the surface normal. Whereas if it is traveling from a denser to a rarer medium, it will bend away from the normal. In this case, because of the shrinkage of the cured part and consequent increase in density, the refraction index will increase, leading to bending the incident lasers towards the center. This will cause some of the laser photons, which would have otherwise been incident towards the outer edge, to be directed towards the center line because of the uh, bending, and thus in the center we'll find a greater depth of curing, and thus CD will increase. There can also be sub-logarithmic behavior, in which the working curve for a given resin material and laser wavelength combination performs below our expected regime. Here, CD increases less rapidly than a simple logarithmic dependency upon exposure to the laser light. And one of the proposed mechanisms for this is because of optical scattering, where you have some microscopic imperfections such as voids inside the resin, which may act as scattering centers. So, say in your layer of resin, you have a void or an air bubble or any other such microscopic imperfection, which is now scattering the incident radiation away from the center. The resultant scattering will then reduce the peak exposure at the center line, thereby reducing CD. And this will result in a decrease in curvature or sublogarithmic behavior. Now we already saw the expressions for the maximum exposure and the maximum depth of penetration. What about the width? The maximum width can be obtained at z equal to 0, and this is given by Cw equals omega naught into under root 2 CD by dP. A few observations about the maximum width of the bead. It is directly proportional to the laser spot diameter, so larger the spot, laser spot, larger the bead width. It is proportional to the square root of the ratio of the cure depth to the resin penetration depth. And again, if you are working within the linear portion of the curve, we can obtain some bound on this maximum width. And in the linear portion of the curve, where CD is between dP and 4 dP, the maximum width will also lie within under root 1 by 2 times twice omega naught to less than root 2 times twice omega naught. Just to recollect, omega naught being the waist radius of the laser beam. Further, we can come up with expressions for the laser scanning velocity itself in terms of the other parameters. Vx is equal to under root 2 by pi p naught by omega naught 1 by e critical e power minus c d by dp. The laser scan velocity is directly proportional to the laser power, as we can see. The laser scan velocity is inversely proportional to the spot size, and the laser scan velocity decreases exponentially with the ratio cd by dp. And while here we have written this equation for as Vx equals some function of the other parameters, typically Vx will be independent. It is some value which we program into the machine and which we specify for our printing process, and it will actually be the other parameters which are determined in terms of Vx. We also have some expressions for the time of curing of a single bead given by T, and that is equal to A by K times under root pi by 2 EC by P naught e power minus CD by dP. What is K? Now here, as you can see, we have several parallel passes going along the x direction, and there is some gap between these passes. In this case also, the gap is constant. This is known as the step over, shown or denoted by S here. Now for a typical process, this step over distance will be some multiple of the laser spot size. Say the characteristic dimension can be the laser spot radius. And physically what it means is, if you are looking at say the top view, or if you are seeing the cross section, if this is one cured bead and this is the center, then distance from this to the next, this center line distance is actually the step over, and typically we take it as some multiple of the radius, laser spot radius. This need not be an integral multiple though, so K is not necessarily a positive integer. It can very well be a fraction, and mostly it will be a fraction because we do not want our beads to be too far apart. We want some overlap to exist between them, for example, to avoid the presence of inter-track voids. And some examples have also been worked out. We'll also work out a couple of examples during our problem solving time. Now let us extrapolate our learnings from a curing of a single bead to the curing of multi-beads. Here, the primary difference is that the behavior for single beads remains the same as in. What we are doing is we are just superimposing two single beads with some overlap to predict the characteristics of a multi-bead print. And here what we'll see is that there are regions of maximum curing depth here and here. These are also referred to as hill features. And then we have this region of minimum curing depth, which is called a valley. Notice that we expect, say, just by plotting two single cured beads, we expect the minimum to have been located somewhere here. But because of the superimposition of energy in this region, which I'm denoting by these dashed lines, it actually shifts down, and thus we have these hill and valley features forming. The difference between the depth of the valley and the depth of the hill is called undercuring depth, or UCD. So the overlapping region will have the maximum exposure at Y in, which is shown by the green point here.
Now assume that the maximum exposure in the hill is EH and that the maximum exposure in the valley region is EV. Therefore, the uncured depth is given by CdP minus CdV as we just saw equals dPLN EH by EV. What is the tolerable limit for such an undercurrent depth? Because when we are printing, we want our part to ideally have sharp features. So we would have wanted this bottom to be, say, exactly flat. But now we are seeing that because of multiple passes, what we can realistically expect is some wavy feature. But how much waviness can we tolerate? Typically, the difference between the depth at the hill and depth at the valley should be less than 5 micrometers for an SLM process. And if it is indeed less than 5 micrometer, then the condition is referred to as planar curing. And for some assumed value of this penetration, depth of penetration, some 15 to 10 power minus 5 meter, the ratio for exposure in the hill and exposure in the valley can be worked out to be less than equal to 1.034 for planar curing. Thus, this is a condition which can guide us in the choice of process parameters and in predicting whether for a given material, for a given working curve, wavelength and energy distribution, whether we'll have planar curing or whether we'll observe large wavy features on our built part. Here the effect of superimposition of multiple such passes is shown, and the cumulative exposure at hills can be calculated using the formula given here, and for the valleys by the second formula. We'll also be using this during the solution of a few example problems, and this visualization really helps us to understand its effect. Here, let us remember that k again is the multiple in the relationship step over distance equals some multiple of the laser spot radius. If this multiple is very large, say for k equal to 6, we see these large features. If it is decreased further, say k equal to 1, we see smaller fluctuations in the surface shown here. At k equal to 0.9, it becomes almost planar. At k equal to 0.5, it is very plain but also very narrow. And at k equal to 0.1, it has a very sharp peak. Now we can also have some other useful expressions. Here again, the zone of influence is discussed in the y direction. And when we are trying to work out the condition for planar curing, we only want to check within this zone of influence. And how it can be calculated is we check at only some integral multiples of k as shown here. This will become more clear when you solve an example and check for the planar curing condition. And we'll also just briefly touch upon a multi-layer, multi-bead print. So typically, whenever we are trying to say optimize our parameters for a new material or a new material and new process combination, we start with single bead. And often you will find a very healthy amount of literature just on these single bead experiments, and lots of insights still coming in and making us aware of complex physics. Then we progress on to, say, single layer multi-bead, as in now you have multiple beads but we are still working in the same layer. Then we can finally move on to multi-layer multi-bead, and this is the same thing which we're doing right now. So ideally, we would like to have uniform curing throughout our current layer so that we can have, say, perfectly flat layers of resin being printed in each step. However, this is not possible in practice owing to the exponentially decreasing irradiation throughout the laser depth because of Beer-Lambert law. And hence, the laser power and layer thickness are so adjusted so as to result in a cure depth which is just slightly greater than the thickness. This is called as overcure. So what happens is, we already saw that, say, for some layer there will be these hill and valley features, and the valley region can be somewhat vulnerable to underexposure, as in here the curing might not be as much as desired. How do we take care of this? For the next layer that we print, we ensure that it is not lying fully above the current layer, there is some overlap. Now what happens is, the previously susceptible region is now getting printed in a region which is already cured, and we do repeat this exercise successively to build a strong part with good mechanical properties. And a similar analog in metal printing, which some of us might be aware of, is the concept of dilution, where, say, starting from principles of metal cladding, when we are trying to deposit a material on a substrate, we do not want all of it to be deposited just on the top. What we really want is some of it to be deposited on the top, and then some of it to also go below the substrate in order to bond well with the substrate. Typically, a dilution ratio of some 10 to 40% is recommended and necessary for having good mechanical properties. And this 10 to 40% can be computed either as, say, the ratio of height of the bead and the depth of dilution, or in terms of the areas of the bead and the area of the dilution, and so on. But essentially, what we want is that there must be some influence of this newly deposited material into the previously deposited layer of the substrate for good mechanical properties. Uh, Now we have discussed all the important formula and concepts that will be required for problem solving. Let us just take a short break, and when we return, we'll solve some example problems that will further clarify these concepts.
seriously more because ऐसा नहीं वो ही also has an offshoot company which is started in Navi Mumbai. They are actually hiring and they are training you. I know that some people लोग वहाँ पे मतलब AI का काम करते हैं, but उनका core area will focus on biomedical informatics design.
So, welcome back to the session. As some of you might be aware, it has been raining incessantly in Mumbai, along with a few other regions of the country. Uh, the conditions in campus are fine, but in Mumbai city overall, the logistics have been hit really hard. So, wherever you are, I hope you and your family are safe. Let us continue our learning. We have some common data for the next few questions. In an SLA system, resin is used in a vat of size zero point 0.2 into zero point 0.2 into zero point 0.4 meter cube, and there are a few other specifications of the system. A 1000 milliwatt laser with Gaussian intensity distribution is used to cure the resin. The laser beam reduces its intensity by 1 by E square at a distance of 200 micrometer from the center of the laser beam. It is desirable to have maximum curing depth to be 3 times the penetration depth, and the spacing between two single beads is 2 times the laser beam radius. We are also supplied with the working curve for this resin and laser combination, which gives us the cure depth versus the exposure. So we already familiarized ourselves with all the various formulae required to solve various questions. Let us just identify the important parameters from this given information. We have the vat, and we also have the scanning size, which will be 0.2 into 0.2 meter square. The nominal power P naught, which is 1000 milliwatts. Then we have the laser beam reducing its intensity by 1 by E square at a distance of 200 micrometer. This will be omega naught. From the center of the laser beam. CD is equal to thrice dp, and the spacing between two single beads is 2 times the laser beam radius. This step over, as we know, is typically some multiple of the laser beam radius. In this case, it is equal to twice omega naught. K is equal to 2. And visually what this means is, if we are looking at the cross section, say, if this is one bead and this is the center, the next bead is located at radius exactly equal to twice the laser beam radius. Now ideally this uh, width of the beam will also be equal to the radius of the laser. So what it means is typically they are just touching each other, but that's not really important. It's just for visualization purposes. We also have the working curve here. So let us now start solving the questions. First, determine the value of the depth of penetration in mils. What we have here is CD versus uh, Emax, or maximum exposure. So this is Emax and this is CD. We have an expression for dp in terms of CD, which is already given in the slides. CD is equal to dp times ln Emax minus ln E critical. Here we have a plot of CD versus Emacs. So DP and EC will remain unknown. Let's see how we can still solve for it. Let us take just a few values of this plot near some standard regions. So we can take at Emax equal to 60. Okay, maybe I should work with a slightly thicker tip. Yeah. Emax equal to 60, which will correspond to a CD value of 4.8. Another we can take at say 100. Which will correspond to a CD value of 6. And let us plug it into our equation. So for the data point 60, 4.8, we have 4.8 equals dp times ln 60 minus ln EC. From the second data point 100,6, we have 6 equals dp ln 100 minus ln EC. Now we see that we have two unknowns, dp and EC, and we have two equations. Thus we can easily solve for them. Also, please note that this is just a straight line trend, so we can use any data point along this straight line. You are free to work with any other data points, and the result will be the same. Say we have equation 1 and 2. If we subtract equation 1 from 2, what we'll end up with is 6 minus 4.8 is equal to dp times ln 100 minus ln EC minus ln 60 plus ln EC. So which implies that 1.2 equals dp of ln 100 by 60 or 5 by 3, which will give us a dp value of 1.2 by ln 5 by 3. And let me just quickly calculate this. This is 1.2 by 0.511, which comes out to be 2.3483, and the unit is mils or milli-inches. Thus, it was just a straightforward application of the formula already supplied to us. The second question is, determine the value of the critical exposure EC. Now EC was the second variable in the equation that we dealt with already, so we can find its value very easily. Say for instance, using equation 2, which gave us 6 equals dp times ln 100 minus ln EC. Yes, that is correct. And we also found the value of dp, 2.3483 mils. Thus, EC is the only unknown and we can easily solve for it. Okay, not a lot of space, I have to be careful, which implies that ln of 100 by EC is equal to 6 by 2.3483, which comes out to be 2.5550, which implies that 100 by EC is equal to e power 2.555, and this EC is equal to 7.7689 or 769. The unit for this is millijoule per centimeter square. The third question is asking, determine the max curing width of a single bead CW. Now, please refer to the slide to find the formula for the max curing width, and we'll find that it is equal to is equal to omega naught under root 2 CD by dP. So the max curing width CW is equal to omega naught or W naught under root 2 CD by dP. Now W naught is already available to us as a given value. It is 200 microns. And we just calculated CD and dP. CD was okay. No, CD is also given to us as 3 times dP, and we already calculated the value of dP. So let us substitute this into the equation. So CW is equal to 200 microns times under root twice into 3 dP by dP, which is equal to 200 root 6 micrometers, and this will come out to be 489.8979, so approximately 898 micrometers. This is the maximum curing width for a single bead. Please note that at every stage we are using information or data that we have values which we have calculated at the previous step. So if during your certification examination or for an assignment you are given such a multi-part question where the values for one question will depend on the values obtained in the previous question, it will be very critical that we are careful and we obtain accurate values, because otherwise it will lead to a cascading error where the error in the determination of one value will ensure that all further values that we calculate are also erroneous. Okay, I think this question got repeated somewhere. Determine the scanning velocity Vx in meter per second. Now recollect again that formula for the scanning velocity was also supplied to us. Okay, it is right here, equation 4, which is Vx is equal to under root 2 by pi P naught by omega naught 1 by EC e power minus CD by dP. So let us use this formula. Vx equals under root 2 by pi p naught by omega naught 1 by ec e power minus cd by dp. Now notice that all of the values are available to us. P naught is already supplied in the question. It is equal to 1000 milliwatts or just 1 watt. Omega naught is also supplied to us. It is 200 micrometers. Or 200 into 10 power minus 6 meters. We found the critical exposure energy, which came out to be 7.769 millijoule per centimeter square. And just like the others, we'll also convert this to SI units. So this will be into 10 power minus 3, 10 power minus 4, so 77.69 joule per meter square. CD is given to us as a multiple of dP, and it is equal to 3 dP. So let us plug in these values and try to find the scanning velocity as a function of all these other parameters. This will come out to be under root 2 by pi 1 by 200 into 10 power minus 6 or 2 into 10 power minus 4 into 1 by 77.69 exponential of minus 3 dP by dP. Let us calculate these term wise. So the root of 2 by pi is 0.7979 into 0.5 into 10 power 4 or 5000 into 1 by 77.69 into e power minus 3 is 0.0498. Let us multiply this out. So this is 0.7979 into 5000 into 0.0498 divided by 77.69. This comes out to be 2.557 meter per second. Now let us try to rationalize whether this value of the obtained scanning velocity is within reasonable limits or not. As we discussed and as Professor Kapil mentioned during the lecture, the typical order of scanning velocity in SLM like processes is of the order of say 10 meter per second. It can of course be higher, but this is a typical order, and the value which we have is 2.56 meter per second, which is indeed of a similar order. So definitely this sounds right. Now that we have the velocity, let us also try to find the time taken for scanning the entire area of the vat. And again, such a formula was already derived for us. Yes, here it is. T equals A by K into under root pi by 2 EC by P naught e power CD by dP. What is A here? A again, please recollect, is the area of the area to be scanned, and K is the multiple of laser radius, which defines the step over distance. S is equal to K omega naught. So let us use this formula. T equals A by K under root 2 by pi, sorry, pi by 2 EC by P naught e power CD by dP. Again, the values are available with us. A equals 0.2 into 0.2 meter square, K equals 2 EC equals 77.69 joule per meter square. P naught, if I recollect, was 1000 milliwatt, or just 1 watt, and CD was equal to 3 dP. So let us just plug in these values into the given formula and find the time taken for scanning the entire area of the vat. This is equal to 0.04 by 2 under root pi by 2, 77.69 by 1 exponential of 3 dP by dP. And if we write this term by term, this will be 0.02 into 1.2533 into 77.69 into e power 3, which is 20.0855. And if we multiply this out, this comes out to be 39.114 seconds. Again, this is a reasonable amount of time given the scanning speed, which was close to 2.56 meter per second, and for a scanning area of 0.2 into 0.2 meter square. Finally, we are asked to find, okay, not finally, there's one more question. We are asked to find the ratio of exposure in the hills and the valleys. And here we will make use of the concept of zones of influence. So first we must find the zones of influence in the hills. So for hills, this can be found as n equals plus minus 2.146 by k. Again, I'm just directly using the formula which are provided by Professor Kapil in his slides. Equals, so plus minus 2.146. The value of k is 2. So this is equal to plus minus 1.073. and we are only taking integral values in this range, so n will come out to be -1, 0, and 1. Thus, if we are to find the cumulative effect of the superimposed energy intensities in the hills, energy at the hills or energy exposure at the hills is equal to e power sorry the energy at -s, 0 plus energy at 0, 0 plus energy at s, 0 corresponding to the three values of n: -1, 0, and 1. And we know that, say, at any given x on the surface, so z equal to 0, E may be obtained as some E max times exponential minus 2y square by omega naught square. And so we can find EH equals some E max times exponential minus 2 minus s square by omega naught square plus E max times exponential minus 2 0 square by omega naught square plus E max times exponential minus 2 s square by omega naught square. And we take E max common from all of these, and note that omega naught is just a multiple of s is just a multiple of omega naught, so s is equal to k omega naught. Then this becomes exp minus 2 k square omega naught square by omega naught square plus exponential 0 plus exponential minus 2 k square omega naught square by omega naught square. And this becomes E max times exponential of, the value of k was also available with us, it is equal to 2. So minus 2 into 2 square is minus 8 plus exponential 0, which is just 1, plus exponential minus 8, and this will be 2 into e power minus 8 plus 1. This is 1.00067 Emax. Next, we must find the exposure at the valley positions as well. For valleys, again, we'll find the regions at which the zones of influence will occur, and for this the expression is we must check for integers in the range of plus minus 2.146 by k minus half. So n will equal plus minus 2.146 by 2 minus half, which is equal to plus minus 1.073 minus half And so we have to check between uh, plus 1.073 minus half and minus 1.073 minus half. The integers falling in this range will be minus 1 and 0. Yes, because the maximum bound is 1.073 minus 0.5, so which is 0.573, which is less than 1. So these are the only two integers falling in this bound. For the values, uh, the value for the uh, cumulative exposure is EV equals the exposure at s by 2 plus the first integer minus 1 times s comma 0 plus e at s by 2 plus 0 times s comma 0 is equal to the energy at minus s by 2 comma 0 plus the energy at s by 2 comma 0. And again we already have the expression for the energy intensity at any given y on the surface. We just substitute it here. This is equal to E max times exponential minus 2 minus s by 2 square by omega naught square plus E max times exponential minus 2 s by 2 square by omega naught square, which is simply equal to twice E max exponential minus 2 s square by 4 omega naught square. But s is equal to twice omega naught, as you already know. So this comes out to be twice E max exponential minus 2 into 4 omega naught square by 4 omega naught square. So this is simply twice E max into e power minus 2 or 0.27067 or 2707 E max. We were asked to find the ratio of exposure in the hills and valleys. So we just need to take the ratio. We already have EH and EV. So the ratio of exposures in hills and valleys is equal to 1.00067 Emax by 0.2707 Emax, which is simply equal to 1.00067 by 0.2707, which comes out to be 3.6966. In the next question, we are asked to find the undercuring depth. And again, the formula is directly given to us. Undercuring depth is equal to dp ln EH by EV, or the ratio of exposure in the hills and valleys. So again, we must make use of a value obtained in the previous step. We already found dp equal to 2.3483 mils. Into ln of EH by EV, which was 3.6966, which is 2.3483 into 1.3074 which comes out to be 3.0702 mils. And finally, we are asked to check if the planar curing condition is satisfied. For this, let us recollect the planar curing condition. So, planar curing condition is said to be satisfied if the ratio of exposure in the hill to the ratio of exposure in the valley is less than or equal to 1.034. What was the value in our case? In our case, the ratio of exposure in the hill to the ratio of exposure in the valley was equal to 3.6966, which is clearly greater than the critical ratio of 1.034. So, the planar curing condition is not satisfied in this case. And there was one more question on transverse electromagnetic modes, but I've already exceeded the time for this session, so I'll just close it here today. Thank you all for tuning in to the live sessions for the course on Fundamentals of Additive Manufacturing Technology. This is Sourav Goswami from IIT Bombay. Thank you, and I look forward to seeing you again next week.